Welcome, everyone, to the 145th meeting of New Directions in Group Theory and Theoretic Categories. Our speaker today is my Warwick colleague, Peize Liu, and the title of his talk is Stability Conditions via Verdier Localization, Nodal Cubic 4folds, and Casey Surfaces of Genus 4.
Hey, thank you for having me here. So today I will be reporting a ongoing work joined with Chunyi Li. We study the stability conditions and moduli spaces on nodal cubic fourfolds. So this is a relatively new thing to construct stability and study moduli spaces on singular varieties. So I will start with recent progress. So in this talk, X will be a projective variety always over the complex numbers. And dBx is the bounded derived category of coherent sheaves. So earlier this year, we have a big result in this area. Chunyi proved that for all smooth projective varieties, dBx admits a Bridgeland stability condition. And so there are more people joining in a subsequent work that they try to generalize this to singular varieties and varieties in families. So this is a work in progress. So I think since the biggest problem in this area has somehow been solved, so there are further directions people can do from here. For example, to study the whole stability manifold of certain varieties, or to study the moduli spaces and see how you can apply these stability conditions. And there's another interesting open question is that we don't yet have a method to construct stability conditions on semi-orthogonal components, for example, the Kuznetsov components. So a lot of cases are still open now. And yeah, as for the singular varieties, oh, by the way, let me define Kuznetsov components for a while. And so we only care about hypersurfaces in this talk. So for a hypersurface, you can have a exceptional sequence of line bundles, but they're not full. So you can extract its left orthogonal, sorry, the right orthogonal, which is the Kuznetsov component, and usually encodes the important geometric information about that variety. So for singular varieties, studies on stability conditions have there are some progresses. Mainly, people can try to induce stability conditions from the categorical resolution of the singular variety. So I think the earliest result is by Ziyang Zhou in 2024. He studied the stability conditions on a surface with ADE singularities. And later, he also did the example of a nodal quadric threefold. And earlier this year, Nicola Vilches constructed the stability condition on a Kuznetsov component for a nodal cubic threefold from its categorical resolution. So this work would pretty much in the similar spirit. So we do the case for cubic fourfolds. So what is exactly a categorical resolution? So firstly, people have those geometric resolutions of singularities, and they want to give a kind of categorical version of this. And here is just the formal definition where you basically take a geometric resolution and you try to make these abstract definitions out of this. We won't use the definition in this talk. They're just here for the information. But we will use a important result about the resolution of nodal varieties. So this is a result of Kuznetsov Shinder in 2024 and simultaneously by I think it's 7 people in 2023. So what they prove is that if you take a variety with a node, then its bounded derived category emits a so-called cramped categorical resolution. This cramped categorical resolution itself is a Verdier localization, and the kernel is generated by a two-spherical object if the dimension is even, and it's a three-spherical object if the dimension is odd. So we have a very good categorical control of nodal category in this sense. And to use this Verdier quotient to construct stability conditions, there's a philosophy behind this story. I think this is those attempts of people trying to compactify the stability manifold. So there are several different approaches. They share this similar spirit, which is that when you approach the boundary of your stability manifold, the limiting stability condition will acquire a set of so-called massless objects. So you have a certain set of objects with zero central charge or zero mass. And then you try to quotient out these objects by a Verdier quotient, and you descend your stability condition to the quotient to get genuine stability conditions on this quotient category. So we have a lot of examples now and maybe some potential applications. So once you have these stability conditions, you can relate what you have upstairs and induce downstairs to see the stability manifold downstairs. And you can look at the Bridgeland moduli spaces. So you take a moduli space upstairs and you do the push forward. You have a map to the moduli space downstairs, and you want to see what properties of this map can have. So a very optimistic guess is that it is a birational map. And if upstairs you have a moduli space which is smooth, then this will often give you these notions of resolution of singularities of the corresponding moduli spaces downstairs. And we will see some examples in this talk. And another interesting thing is that you can try to put your nodal variety into a family and to study how the moduli space or stability condition changes when you degenerate from a smooth variety to the nodal variety. There is another approach, and it's by a paper just came out yesterday by Chunyi Li and Tianle Mao. So they did this tilt stability conditions in families for final 3folds. Basically, they proved that these singular Kuznetsov components of final 3folds, they have the stability conditions. So that's a kind of a different approach. So as promised in the title, the talk is about nodal cubic 4folds. So in this case, the result is that the Kuznetsov component of a nodal cubic 4fold can be expressed as a Verdier localization. Here, you have a derived category of a K3 surface of genus 4, quotient out by a spherical object, which is a spherical bundle on your K3 surface. And we can state our main results here. So just a spoiler is that you can choose a tilt stability on the K3 surface or limiting tilt stability. It defines you a weak stability condition. And then it induces a stability condition on the Kuznetsov component of the nodal cubic fourfold. And for the moduli spaces, what we can say is that if you take a numerical character on the Kuznetsov component, you can choose a lift of the character on the K3 surface, and you have a birational map from the Giesecke moduli space to the corresponding Bridgeland moduli space of semi-stable objects corresponding to this stability condition. And moreover, we can describe this birational map as a sequence of flops followed by a divisorial contraction. So these are the stories of wall crossing on the K3 surface, which we'll see later. Okay, so that's the introduction. Any questions so far? Okay, if no, let's go through some formal stuff on stability conditions, go through the definitions and some things, just the boring things. So what is a stability condition? People sometimes think that as a generalization of the slope stability on vector bundles. So you have this notion of stable objects on a triangulated category. So the setup is as follows. You have a triangulated category of Gaussian linear, and you consider its Grothendieck group. And you will start with an abelian category. So here, this abelian category would be the heart of the bounded T structure on D. So you could think of D as a dB of X, and A would be coherent sheaves, cox. So what is we define a stability function or a central charge on A. So it's a group homomorphism from a certain lattice, finite rank lattice, to complex numbers, which has image in the upper half plane union the negative real line. Or in other words, it has phase from 0 to 1. So this phi is called the phase of the objects, and m here is the mass for if E is semi-stable. And so this is a weak stability function. So if you further require that every object, non-zero object has non-zero mass, then we call this a stability function. And for this function, you have a notion of stable exactly as for slope stability. We will try to compare the phase of the objects. So it's called semi-stable if for every non-zero proper subobject, the subobject has phase smaller or equal to the quotient. Here you need the quotient because you should be careful about the massless things. And of course, you can define a slope as usual and try to compare the slopes, which give you the same information. So let's define the stability condition. So it's not very difficult, just that we have a triangulated category, we have a heart of bounded T structure, and we have a weak stability function on the heart of bounded T structure. We further require that it satisfy the Harder-Narasimhan property, which basically says that you can build every object out of the semi-simple objects, the semi-stable objects by filtration. So far, if you're choosing a weak stability function, then it would be a weak pre-stability condition. So if we want to drop the word pre, then we would like it to satisfy the support property, which is the notion that gives you a good theory of later we'll see the deformation and moduli spaces. So the support property says that You can choose a norm on the lattice tensor with R. There exists a positive constant such that the norm of these objects is bounded by the central charge times a constant. Here we slightly modify the definition of the support property by quotienting out the saturation of the sublattice generated by the kernel or generated by the massless objects. This is because if you want a stability condition on lambda, then you cannot have massless objects. It will violate our definition, but because we're doing deformation on the tilt stability space, it's more convenient to think about this as the correct notion of support property. Okay, so this is for the stability condition. And the famous result is that when you try to consider the set of stability condition on the triangulated category, the result of Bridgeland says that this set can be equipped with the structure of a complex manifold with dimension equal to the rank of the lattice, in the sense that the forgetful map sending a stability condition to its central charge is a local homeomorphism. So basically, you can deform a stability condition just by deforming its central charge. This is like the starting point of the whole theory and why we love it. And as promised, we are trying to see how the stability condition behave on the Verdier quotients. So recall that we say the slogan is that we want to quotient out the massless objects to get a stability condition downstairs on the Verdier quotient. So here is precisely what we mean. We take a Verdier quotient from T tilde to T, and we assume that you have a weak pre-stability condition upstairs, satisfying that the kernel of the central charge is equal to the kernel of the Verdier localization when you restrict them to the heart of bounding T structure. So in this case, you can check that when you intersect A with the kernel of Z tilde, this thing gives you a subcategory. So in this sense, when you try to see the image of A tilde under the Verdier localization, this would be a Serre quotient like this. So the good thing about the Serre quotient is that it is exact, and the image would be an abelian category, which is the heart of bounding T structure of T downstairs, not T tilde. So this is on the heart level. So for the central charge, since for Verdier quotients, the corresponding map on the Grothendieck group is surjective, and you have this condition, so you can induce from Z tilde to a unique Z satisfying this compatibility equation. So the proposition is that you can check that these data, the heart A and the induced Z, will define to you a pre-stability condition on the category T. And it has some more good properties. For example, if you take a semi-stable object upstairs, then the push forward would be still semi-stable downstairs. And conversely, if you take a semi-stable object downstairs, then you can lift it to some semi-stable objects upstairs. And I think similar results have been obtained in some slightly different forms across different papers, but this is completely formal stuff. Okay, so this is the formal theory. Any questions so far? Am I going too fast or not? Okay, so maybe let's continue. So now we focus on the main example we do, which is the nodal cubic fourfold and K3 surfaces. How are they connected? So this is a very classical geometric setup. I think it's due to Kuznetsov in 2010. So you will first take a cubic fourfold and with a node P and smooth otherwise. You can always choose coordinates to represent the cubic fourfold in the following equation form, which is very explicit. Of course, you want to resolve it by blowing up along the node. So this will give you this blow up diagram here, where sigma is the blow up and Q is the exceptional divisor, and y tilde is the resolution of y. And of course, we have another half of the diagram, which is that if you consider the rational map y to P4 by projecting away from the node P, it's also got resolved or got lived to a real morphism from y tilde to P4. And we know that on the right-hand side, it is also a blow-up diagram where y is isomorphic to the blow-up of P4 along a K3 surface. The K3 surface is the intersection of the equations f and g. So for nodal cubic fourfolds, both f and g would be smooth. So x23 here is also smooth, and it's a degree 6 K3 surface, so it's genus 4. So geometrically, you could think of this K3 surface as the point on K3 surface as lines in y passing through the node P. So the exceptional divisor of this K3 surface, which is D, is the union of all such lines. So this is kind of a universal family. And so somehow you can relate these nodal cubic fourfold and the K3 surface through this geometric construction. And then there is the categorical construction also due to Kuznetsov and the 7 people here. So what they show is that the Kuznetsov component of the cubic fourfold actually emits a crescent categorical resolution by the category, the derived category of the K3 surface. So you have a very explicit functor here. The kernel is generated by sigma. And actually, the sigma here is the restriction of the spinor bundle from its defining quadric. So you could think of its defining quadratic as Q via this identification. And and there's this rank 2 spherical spinor bundle on Q, and it has this Mukai vector on the K3 surface. And using the theorem I mentioned in the introduction, they show that this is in fact a Verdier localization. So, which means that if we know the stability conditions on the K3 surface, we can descend them to the Kuznetsov component. So the next thing is to study the tilt stability on K3 surfaces. We have not defined what the tilt stability is in general, but roughly for surfaces, they cut out a two-dimensional slice of the stability manifold. And for this K3 surface, you could think of it in terms of its heart as so the heart itself is the extension of things in how to say that? Let's write it down. It's the extension of T and F shifted by 1, where T is the object with slope bigger than beta, and F is the subcategory of the objects with actually I think we need this to be the minimum slope, minimum slope of the HN factor. Yeah, and so this is tilting of the heart, and you have the central charge given as follows, which use the Chen character of the object. So we often when we think of tilt stability, we often think of the diagram like this. We represent it in a two-dimensional plane where every point corresponds to a tilt stability, the parameter of the tilt stability, and simultaneously it corresponds to a object, the Chen character of an object via the kernel of the central charge. So, for example, we know that the spherical object has this Mukai vector, which means that it has rank 2. Chen 1 is minus h, Chen 2 is 0. So this corresponds to a point minus 1/2 0 on the diagram, which is exactly this point. And you can see every point here defines a stability condition on the K3 surface, but on this point exactly, this cannot be a stability condition because sigma lies in the kernel of that central charge. So when you deform your stability conditions from a general point to this point, the limit will be a weak stability condition. But you can manually check all the assumptions we gave when we have those formal lemmas, and you can check that it satisfies every condition you have. So the result is that the weak stability condition defined at this point gives you on dB of x23 gives you a induced stability condition on the Kuznetsov component by your Verdier quotient. Yeah. So we have now the induced stability condition. The next thing is to consider is the moduli spaces. So when you think of moduli spaces, you usually fix a numerical character. So downstairs on the Kuznetsov component of y, you can always lift this to the numerical character on the K3 surface, because on the numerical level, this is also a quotient. So you could think of this as this quotient. But now you have the ambiguity of lifting, so you can choose any V tilde upstairs. And there may be a best lifting that gives you the good notion of morphism between moduli spaces. So you can look at it at different levels. For example, on the numerical level, you want this source has as large dimension as possible. The largest point you can get is when V tilde is orthogonal to sigma numerically. This is on the numerical level, and on the object level, can you so under this Verdier quotient, is there like a distinct representative upstairs? Or can we say that is there a section of the Verdier quotient? It turns out that for this quotient by spherical object, there is such notion. So we call object is sigma normal if the R home of sigma to F is concentrated in degree 0. And you can take any object by taking cones and co-cones, you can strip off all the other degrees to get things in degree 0. So the observation is that every object has this unique sigma normalization. So in this case, you can think of this normalization as a section of that Verdier quotient. Another thing is that there is an ambiguity of this sigma here, because recall that we have this two-dimensional plane of stability conditions. You have a generic stability condition anywhere here, and they're related by wall crossing, and you have a weak stability condition here. So what exactly, which sigma are we talking about exactly here? So to answer this, we'll look at the wall crossing theory on K3 surface. So I think this is by the famous work of Bayer-MacLeay. What they show is the wall and chamber structure on the K3 on the stability manifold, and how you change how the objects and moduli spaces change when you cross a wall. So let me draw this diagram here. So suppose that we have a character V tilde here. On this plane, the walls are linear, so they look like this. So for point very high up here, it's called the large volume limit. So the moduli space would I would say sigma infinity, say. So this would be simply the Giesecke moduli space that we are familiar with. they parameterize the Giesecke stable sheaves. And whenever you cross a wall, the moduli space changed by a flop. So so the walls are locally finite, and in the end, the last word would be the wall connecting v tilde with sigma. So let's say a generic stability condition on the wall. Let's denote this by sigma L. So we can state the result as follows on the wall crossing. There are birational maps where after a sequence of flops, the final map, which in this diagram, you start from some stability condition above the wall, and you move it onto the wall. This will give you a divisorial contraction with the exceptional locus, exceptional locus given exactly by those objects where there's non-zero home from sigma to f. And it turns out that the stability condition on the wall gives you the right thing to consider when you try to do the inducing stability condition downstairs. So it turns out that on the wall, the moduli space is isomorphic to the moduli space of sigma bar semi-stable objects on the Kuznetsov components downstairs. So this tells you that you can study the moduli space on the Kuznetsov components by studying those on the K3 surface, and for those on K3 surface, they are given by this biametrically wall crossing story. So this is a pretty nice story. Okay, any questions so far?
Could you just outline why this moduli space is same for the K3 and the Kuznetsov component? That stability condition.
Sorry, which condition are you referring to?
The proposition at the end of the page.
So this one.
Yeah.
Yes, so we can see it more clearly in the example later, but the idea is that this divisorial contraction here forgets about the extensions data here, because you on the moduli space parameterize as equivalent classes of semi-stable things. So if you have an extension like this, all such extensions will be contracted to polystable objects like this in this moduli space. And on the things downstairs, what you do is under the Verdier localization, these things get killed. So these things get killed. So they will be mapped to just f prime in this. And you can show that on level of S equivalent classes, there is a one-to-one correspondence between these objects and these objects. And it would be trickier to say that this is actually an isomorphism. So there's some technical details. Yeah. Okay. Does that answers your question? Yeah, I mean, we can see this more clearly in the example. So we'll discuss this particular example of final varieties of lines. So let's go back to this picture and think about the Hilbert scheme of 2 points on the K3 surface. And for technical reasons, we'll assume that the Y does not contain a plane. So recall that we say that this K3 surface parameterized lines in your nodal cubic passing through the node P. And the question is, what does the Hilbert scheme of 2 points on K3 surface parameterize? Well, that's very simple. It parameterizes 2 lines on the nodal cubic. So there are 2 ways. So if Z is a reduced length 2 scheme, then it defines 2 lines in Y passing through the node. If it's non-reduced, then it defines a double line passing through the node. But either way, they define a plane in the P5, which is where Y lives. And you can intersect the plane with Y. So the intersection will give you the union of 3 lines or the double line union 1 line. So the residual line here, which is LZ, so we will have this assignment from the length to subscheme Z of the K3 surface to the residual line LZ. So this will define a map from the Hilbert scheme of 2 points to the final variety of lines on the nodal cubic. And I think Hassett is the first person studying this map. He showed that, okay, this is actually a blow-up map. So it is the blow-up of the final variety of lines along a copy of the K3 surface itself. So you could think of it separates all the how do I say it? So this embedding is given by the interpretation that every point on the K3 surface is a line passing through the node, and for each line passing through the node, there is a transverse double point singularity along the final variety of lines, and this blow up resolve that singularity with the exceptional divisor psi here. So some people call it the trident divisor, and there's a lot of equivalent characterization of that divisor. So you could say that it's where the line passed through the node, or in in X23, the subscheme Z defines a line that is contained in the quadric, or another way to say that is the line intersect X23 in 3 points. And there's one more interesting characterization is that this is exactly the same locus as those ideal sheaves with non-zero homes from sigma. And this condition will give us a modular interpretation of the geometric result. So geometrically, what is the, in terms of the moduli space, what is the Hilbert scheme of 2 points? So you could think of the ideal sheaf of these subschemes. And they are Giesecke stable, and they form a Giesecke moduli space, which is isomorphic to the Hilbert scheme of 2 points. So in the diagram, let's denote this by V tilde. A V tilde is exactly a character here. So in the infinity, you have this Giesecke moduli space. And what happens is that you only have one wall, which is the wall joining V tilde and sigma. Let's denote this wall by L. So when you cross the wall from above, these non-zero maps from sigma to IZ will give you a destabilizing sequence with the so this is a short exact sequence in the coherent heart, and with the object here is the ideal sheaf of a point twisted by minus h. So the point is exactly the point in the K3 surface that corresponds to the residual line, as we see in this. Yeah. Okay, so what happens to the moduli space itself is that this gives you a divisorial contraction. Which contracts all such extensions, which are these objects, to the S equivalence class represented by these polystable objects, IQ twisted by minus h direct sum sigma. And on each point, this is a P1 bundle. So geometrically, this contracts the trident divisor to X23. And in fact, this divisorial contraction is exactly the map, the geometric map phi. So we see that on the wall, if there's a stability condition here, sigma L, the moduli space with respect to stability condition sigma L is isomorphic to the final variety of lines on Y. And by the theorem before, it is isomorphic to the Bridgeland moduli space on QY with a certain character lambda 1 here. Well, the next question is, what exactly is lambda 1 numerically, and what objects does it parameterize? Then after a lengthy calculation, you will find something very horrible. So if for those lines which does not pass through the node, things are very good. You end up with something called FL, where FL is exactly the projection of OH into the Kuznetsov component. So this is exactly the stable objects you would expect in the smooth cubic fourfold case. And you can show that these are perfect objects. So these are perfect complexes. They live in D-perf. But for those lines pass through the node, or for those contracted by this divisorial contraction, you'll get something very horrible. So according to my computation, this will be a three-term complex here. And this is not a perfect object. But regardless of the specific form of the object, at least you know that the final variety of lines now is isomorphic to a Bridgeland moduli space on the nodal cubic fourfold. So another interesting question from here is that, is there a way to put this into a family? So say you have a family of cubic fourfolds over a base, where the general fibers are smooth cubic fourfolds, and the special fiber is this nodal cubic fourfold, and you have this Bridgeland moduli space in family. Can you put that in a family in a way that the special fiber is the moduli space we describe here? So I think that would be a a very tricky thing to consider. So we don't know yet if this stability condition induced by Verdier localization can be put into a family for those stability conditions like the constructed by using conic fibrations, as in the work of Bayer, Lauth, Macleay, and Stellari. So it's an interesting thing to consider. And another thing we are still doing is to study some other moduli spaces. For example, the LLSVS eightfold can try to see what the character is and what objects it parameterize for this nodal cubic 4-fold case, and then now it's still a work in progress. I think that's it for today. I think I might have gone through this too fast, but please ask me any questions. Yeah, thank you.
Thank you, Peize. Let's all give this big round of applause. Okay, if you have any questions for the speaker, please ask them now.
So can I ask a question? So I would expect, I mean, because you are saying that this divisorial contraction, this map is given by this wall crossing on this case-free surface, right? Because you identify this moduli space on the Kuznetsov component with this m sigma L10-1. But
Yes.
But it looks like a priori one could expect that this morphism should given by this this pi lower star, right? I mean, if you take like ideal shape of Z in this modular space, can you compute this just pi up pi lower star to this IZ? Then you get an object in the Kuznetsov component downstairs. So is this functor will induce this this map phi?
I think it will induce such map, but it will not be a isomorphism anymore. So I think it's very tricky to think about this modular space because it's a modular space of a weak stability condition. And I think the expectation is that this thing should be the same modular space as the one slightly above it. So this thing, I think the expectation is that this should be isomorphic to the one above it. And there is a subtle issue about treating the semi-stable locus and stable locus. So I think this is also another point because this map is not directly induced by pi lower star. So I think for us, it's very clear that you have the bijective, you have the bijection on the level of S equivalent classes, but to upgrade this bijection to an isomorphism, maybe it's slightly tricky, and we are still trying to find a way to argue it technically. I think there will be some local computations.
Okay, thanks.
Yeah, thank you for your question.
And also, I have another question. So for this picture, I mean, because you can still do some like categorical resolution for this higher dimensional, this nodal cubic, for example, this nodal cubic 5-fold, then the resolution derived the category of a 3-fold of degree 6, right? So in that situation, you should also have the same picture. You have this induced stability conditions.
Yeah, I think so. I think I will try to write that in my thesis if I have time. But yeah, it depends.
Okay, thank you.
Yeah, but I expect the same story holds also for nodal cubic nodal cubic 5-folds. But if you have even higher dimension, like 6-folds, then you don't know what stability conditions are on upstairs. So this will break down.
Thank you again, Joshua. Any other questions?
I'm kind of curious. You had this lemma a while ago about like sigma normalization, every object
Yes.
had a lift with Holmes only in degree 0 from the spherical object.
Yes.
I was wondering the argument for this lemma, is this pretty easy or?
I think it's quite easy because you're basically like repeatedly taking cones to get rid of the R homes from the top degree and the lowest degree. So you kind of do this induction to until it only have 1 degree remaining.
I see, okay.
Yeah, and basically what we use is only the property that R home of this spherical property for the R home of sigma. And this is for 2 spherical objects. So we have a version for n spherical objects. So for n spherical, what you get would be something concentrated in n-1 degrees.
So for 2 spherical objects, you'd expect something concentrated in. Okay, so you're saying in n-1 different degrees.
Yeah, n-1 different degrees. And for this, you can have support only in 1 degree.
Because I thought if you have a 2 spherical object, you can kind of bring morphism from degree 2 down to degree 0 and so on, but then you can't really bring morphism from degree 1 down to degree 0. But this is probably me missing something obvious. Don't worry, maybe we can talk later. It's fine.
Yeah. We can.
Thank you, that was helpful.
Yeah, I need to look at the details of the proofs more closely. But I think this should work for n spherical things.
I had one other question is
Yeah.
so if you wanted to consider maybe like type A2 rather than type A1 singularities, you could have 2 spherical objects in the kernel. Do you think you could have an analog of this kind of idea with multiple spherical objects or?
As long as so for the A2 singularity, are you referring to cubics only or for any variety?
Yeah. So I mean, I'm imagining even surfaces, but yeah.
Okay. Yeah. So I'm not sure because for I know that for A2, so for cuspidal cubics, you can have a kernel generated by 1 or 2 spherical things. But for two spherical things or multiple spherical things, we might not have a good normalization like this. So in terms of the moduli space, it will not give you a very nice isomorphism, maybe. So you cannot have some kind of injection somehow, but I think surjection yeah, I don't know, but it's a very interesting question to consider when you have a more complicated kernel and what else could you expect? Yeah.
Sorry, I have one
Yeah,
more
we can
question.
discuss that later.
Can you just turn this slide to the end of this? You say you have 2 types of object parametrizing. Yes. Okay. So, okay, let me take a picture. Thanks. Yeah.
Yeah, I can share the slides afterwards. Yeah.
Okay, maybe there is one small question. So for the low dimensional case, for example, this cubic threefold case, I think the categorical resolution is not derived the category of a curve, right? It has a semi-orthogonal decomposition with an additional exception object. So in that case, do you have the similar picture like this wall crossing? Have you ever considered about?
I mean, I guess Nicholas Wiltshire may have some idea about that because that's his work. And I think the idea is that upstairs you have this derived category of coherent systems and stability conditions on a coherent system. And they also have like a 2-dimensional slice. And but I have not looked into the detail of that. But I think it may be similar stories.
Thank you again, Visual. Yeah, do send me the slides page if that's okay.
Yeah, sure.
Along with the I don't know, the notes that you wrote on them as you were doing it.
Okay.
Any other questions, anybody? What was the eightfold you mentioned at the very end when you were talking about these other modular spaces that you were considering?
Sorry, what point?
At the very end, you mentioned an eightfold. I don't.
Oh,
Can
so it's the LLSVS eightfold. So if you think about the moduli spaces on a smooth cubic fourfold, the four-dimensional one is this final variety of lines, and for the eight-dimensional one is the LSVS eightfold. And I think for the wall crossing story, it's already studied by some people, and maybe we can try to interpret this in the framework of this inducing stability conditions downstairs.
Thank you. Any other questions, anybody? If not, let's give the speaker a round of applause again.
Yeah, thank you.
Thank you very much all for coming. We have Daniel Lapardini Fragoso. I hope I said his name correctly next week. Bye.
Bye.